pigeon. E. Okay, and so what we want to do is see if we can get the column. So I think we do select. Which select is this? I have no idea. Okay, cool. So select 0, 0, G. I think if we did 1, 0, we would get 1, 4, 7. Yeah. Okay, so the way this works is like 0 and 1 are either in a two-dimensional situation. Hang on. Oh, sneezy. Sorry. Okay, so 0 or 1 in a two-dimensional sense is like get the column or the row. Or sorry, the row or the column. And I think if we did 2, this would just like fail. Yeah, because it's a two-dimensional thing, so it can't really do that. If we did 1 here, we would get the second row or column, excuse me. So 2, 5, 6. Okay, so over here we can use select 0 will get rows of two-dimensional tensor. Select 1 will get columns of 2D tensor. Perfect. Okay. So that was step 1 for today. We needed to know how to do that. Next thing is seeing if we can figure out how to do inverse. I don't know that we ever came up with a good solution for this. Hey, Abby, what's going on? I don't think we came up with a good solution for this. Did we? Nope. Hang on, sorry, I gotta go get my notes. I didn't bring those up yet. Like a goofball. Oh, we didn't want to do inverse. We wanted to just do linear system. So let's look that up. Hey, Clark. Inverse. So if you look for matrix, inverse, Wolfram alpha. I think this is probably maybe the right way to do this. What's the... What's the tool where you the documentation? Wolfram math matrix inverse. They have like a ton of but this is like an example. Maybe it's this one? Yeah, this is what I'm looking for. Math world. So that's what an inverse is. So basically you're solving this equation. Oh, maybe we can do that then. Maybe we can solve that equation. I don't know yet. So let's go. We got to go look at the solve thing. So I think that if we go back up here and just look up solve, maybe. Lin alg solve, Cholesky solve. Self. A. Okay, that's not very helpful. So let's look at the PyTorch docs. For 1.9 solve. Okay, so we need to give A and B, which is the solution. So the solution is just ones, and the input is A, but we need to solve something that's actually invertible. So I think I have an example. I don't know if I have an example. So let's see if we can do this in Haskell. When will we learn to create parallel universes? We will never learn how to create parallel universes in Haskell. The reason for that is mainly that we're not interested in universe-sized problems, right? Or the existence of parallel universes. So is P determinant P? Okay, so I think P is invertible. So what we want to do is say Q is a tensor. And I think we can just use ones here. So ones like will generate a ones matrix similar to whatever you have. So like I know the dimension of this is this. So if I wanted to solve for the inverse, I think that we can just do that. Oh, that's not a ones. That's not a diagonal ones. Uh, okay. Hang on. There's got to be a way to make a diagonal matrix of um tensor options. What are tensor options? This just defines the types. This doesn't define anything about like whether it's diagonal. I returns a 2D tensor with ones on the diagonal and zeros elsewhere. That's what we're looking for. But we can just do um it would be really nice if we could just make a what's it called? I. I. I've never heard this term before. Okay, anyway. So apparently we use a function called I, and I. Oh, maybe there's something called identity. Um, PyTorch identity matrix. Yeah, that's what it's called. If input is a vector, oh, I guess we could call diagonal on it. Diag flat. So we could just say do ones and then take the diagonal. So we could do ones like P and then diagonal, I think. Isn't that what it was called? It was here. Diag dim. Okay. Didn't I do this once? I'm genuinely a little confused about what this means. Anyway, maybe we should just use eyes. Whatever. Do that. Okay, so I is certainly not a tensor. Where'd it go? And we need to take a square and we need these tensor options, which I think is just default ops. But we need to change its D type to float, I guess. Okay. So with D type float, to with D type float default ops. Okay. So we need tensor factories. We need with D type. We need default ops. Okay. All right. And then let's just put dot there, I guess. And let's see if this works. I've not done this before, obviously, so we're still learning. But there we go. So there's a square float D type tensor. You'd think that there'd be a less annoying way to do that, but okay. So there we go. So what we want to do is now try to solve. So let's see if we can get inverse of P, which is going to be a tensor. So the inverse of P is solve, and we're going to be given P and the output Q. Okay, so this returns two tensors for some reason I don't understand. And then inverse. Okay. Torch solve is deprecated in favor of linear. Okay. All right. Um. Sure. Uh. So we want lin alg solve, I guess. And what does lin alg solve give us? A tensor. That's kind of funny. Okay, there we go. And if we take P, if we matmul P with inverse of P, we should get 1. Is your cat called Schrodinger? No, I don't. My cat's names are Layla and Andre 3000. Obviously, there's some floating point goofiness here, but like that's totally fine. It's pretty close. So there we go. So basically solving a x equals 1 x will be the inverse of a. It only exists when determinant a is not equal to 0. Guess we can stick these like okay. And determinant a not equal 0. Cool. So I think that if we tried to do, if I recall correctly, the determinant of g is exactly 0. So we should not be able to take inverse of g. And over here we need so we need a 3x3 floating point matrix, or sorry, a 3x3 ones matrix. So maybe we should call this like literally 1, 2. I don't know if we're gonna need this again, but we might. So let's just do that. We could also write like just a function that takes an integer and does this as well, obviously. Okay, so if we reload this and we try to do inverse of g, this should fail. And it should say something like the determinant is 0, which is this. That's what this exception means. I don't exactly understand the U at the moment, but anyway. So this will fail because determinant G is equal to 0. Okay, cool. So we did this. So we also, okay, so let's also solve the linear system we did earlier. So we need two matrices. This will be a Q, which is a tensor weighting. You can property test this, perhaps. Property test. Well, like, so what I'm thinking when we get further along is that we're going to have different types of tensors, which are just new type wrappers around tensor that just describe the properties of it so that we can like handle certain situations. So like if, hey Joker, if a matrix is Hermitian, then we'll have like Hermitian tensor or something. And then if it's or I don't know, have a bunch of properties or like maybe have like a MTL style constraint thing that says, you know, the matrix to this must be Hermitian. I don't know, something like that. We'll have to see, but okay, so anyway, we need Q and R. So this is going to be a as tensor two-dimensional, and it's going to contain 1, 7, -2, -9. And R is going to be a vector with 4 and 2. And then we're going to basically lin-alg solve these things. So we should be able to write lin-alg we need lin-alg solve, which comes from lin-alg solve QR. And oh, I must have wrote this upside down when I was doing this before. I did write it upside down before. That's kind of funny. Oh, so anyway, just quick. Let me turn this on, and I'll show you that we just did this recently. So here is the remarkable again. So here's that lin-alg solve. We did it by hand from the book, and you can see there's the solution. We did it obviously via algebra, but you know you could have larger systems of equations, and we can just use this lin-alg solve function to solve our problems. So anyway, let me reorganize a little bit because I think we're going to start the next section now. So now we have something like that. Okay, so now we're going to hop into the next section, which means I need to reorganize my desk a little bit because Like, my desk is really not set up well for the remarkable. Well, and the book for that matter. Okay, so here we go. That was fun. Okay, so let me move this down, maybe to like here, and hopefully you can hear okay. If you have problems hearing me, just put it in chat. I'll try to look. All right, so eigenvalues. Eigenvectors, functions of matrices. Okay, so the matrix vector product AX equals B constitutes a transformation of the vector X to another vector B. B can have a different length and a different orientation than X. An important problem is, given a matrix A, to find out whether vectors X exist for which AX points along the same direction as X. So let me write that in words. Transform X to B via A, I guess. B may have a different length and orientation. Okay. What if I don't really want to write it that way, I guess. So like what if we want B to point in the same direction as X? I don't need to write. Okay. Obviously, not all arbitrarily chosen vectors have this property. In other words, given a matrix A, the question is whether vectors X exist for which all right, so this is some scalar value which, or well, I guess that only changes magnitude. Not direction. Right? So if we had this little guy, then this thing can point in a different direction. But we're saying we're solving for this here instead of X. So X is known. And we want to determine this lambda here. Or wait, no, X is not known. Only A is known in this case. So we're looking for X and lambda such that this equation holds, I guess. Okay, so we could write this in another notation, I suppose, which I showed before, where we write like A box X equals X lambda. Okay, so it says in this way, lambda X points along the same line as X, but it might have a different length. And lambda is not equal to 1, right? Or point in the opposite direction. Lambda is negative. In this equation is called an eigenvalue equation. Lambda is the eigenvalue, and X is the corresponding eigenvector. Note that if X is a solution of this equation, then Cx, with C being an arbitrary number, is also a solution. The eigenvectors can always be chosen to be normalized for convenience. Okay, so again, there exists a trivial solution x equals 0. In the following, we seek solutions x not equal to 0 and assume the matrix A is square. One possible way of finding solutions to an eigenvalue equation is the following. Okay. So let's see if I can make sense of this. So we're going to say x lambda. Again, x is a vector. Lots of dots there, but hopefully you get the idea. It's basically an I's matrix multiplied by lambda, right? It's just written in a different way. It's that. Yeah, or another way is like this. Right, symbolically. Okay. So now we subtract lambda 1x on both sides of equation. Which one's B8? Okay, it's just the eigenvalue equation. So this is still eigenvalue equation, right? So we're going to subtract this from both sides. So subtract lambda 1x from both sides. And then I'll just write this symbolically because I'm not going to write all these dots. It's kind of annoying. But we're basically going to have a minus lambda 1 x equals 0. So the last equation is a homogeneous linear equation, which has only non-trivial solutions. If the determinant of the coefficient matrix is 0, this yields an equation for lambda, namely determinant a minus lambda 1 equals 0. I'm not going to write all the components, but essentially you're just subtracting lambda along the diagonal of A, right? Because this is a scalar matrix subtraction. So, yeah, fine. I'll just write. So, like this here, just to be clear, is like A1 minus lambda A1 2 ... right? And then A2 1 and A2 2 minus lambda ... Okay, and then you can just continue. So you're basically just subtracting the lambda across along the diagonal down. Yeah. Okay, so we have that equation. Let me just rewrite it one more time up here. So determinant a minus lambda 1 equals 0. Okay. So by evaluating the determinant, one gets a polynomial equation for lambda that is of the order n when when A is an n by n matrix, the so-called characteristic polynomial. There are n roots for this polynomial, counting k-fold degenerate solution k times. When an eigenvalue has been determined, it can be subtracted on the diagonal of A, and the resulting homogeneous equation system can be solved for the eigenvector. In practice, numerical algorithms are used that yield the eigenvalues and eigenvalues simultaneously. Okay. Because there are n eigenvectors for an n by n matrix, we can write them together as column vectors in a matrix X. If we collect all n eigenvalues, lambda sub I, in a diagonal matrix capital lambda, we can write n eigenvalue equations for each eigenvalue lambda I simultaneously. Okay, that was like a mouthful, but the basic idea is you can write the following. This is a capital lambda, if that's unclear. So this, oops, collects eigenvalues, collects. I can spell, I swear. I wonder how many spelling mistakes I've made so far. Eigenvalues, lambda sub I, where an n by n matrix A has n eigenvalues. Okay. X collects. Are they rows or columns? Column vectors. Column vectors of eigenvectors. Sounds weird to say column vectors of eigenvectors. So let's say collects eigenvectors in columns. That would be probably a way easier way to say that. Eigenvectors along its columns where there are in eigenvectors. Okay. So cool. Are people following along? Is there any questions so far? How are we doing? Symbolically, we can write this in a different way again. So, right, here's a box. Here's a box. Here's a box. It's really hard to write that one, but let me try and do it a different way. Like that. Okay. Okay, so it says, note that capital lambda is not the same as lambda 1 because it collects all the eigenvalues on its diagonal. Yeah. So, yeah, lambda 1. Let's just, no. Hard to write a capital lambda. Is not the same as lambda 1 because lambda 1 is a single eigenvalue across the diagonal. So this is, right, this is that's a good distinction though. Okay. So, there we go. Yeah, this is always funny. So it's important to note that the right-hand side, so let me just write this, AX equals X lambda. Okay. So often you'll see people write it for Schrodinger's equation, H psi equals E psi. Okay. But mathematically, that's not correct. The correct, so E here, these are the eigenvalues and they correspond to energies. And then obviously psi is the eigenvectors of the Hamiltonian, this H, which is called the Hamiltonian operator. We'll talk about this stuff later. But you'll often see people write this, and mathematically that's incorrect. It should be written, so this is wrong. It should be written H psi equals psi E. Just a note. Okay. All right. So let's do a eigenvalue problem by hand, and then we'll do it on the computer. So 3, 1, -2, 0. So first, we want to get a minus lambda 1, which is equal to 3 minus lambda minus 2, 1, negative lambda. Okay. Now we set the determinant of this matrix to 0. The determinant of a 2 by 2 matrix is the product of the diagonal elements minus the anti-diagonal elements. So we're going to say 3 minus lambda, minus lambda. Anti-diagonal elements are just minus 2 times 1, but we have to subtract them, so it's just going to be plus 2 equals 0. And then we can solve for lambda. There's a picture here, which I'm trying to interpret real quick. Hang on. We can probably skip that for now, I guess. Yeah. So you just distribute, and so you end up with a quadratic equation, lambda squared minus 3 lambda, right? Because you just distribute this. Again, I have no idea how much math people have done, so just be clear. I mean, I haven't done this stuff in a while. And then you could solve for this. I haven't even solved a quadratic equation in a long time. But you can get lambda 1 is equal to 1, lambda 2 is equal to 2. And then you plug in this equation. Yep. So you plug in these. So plug these into a minus lambda 1. So we have two solutions. 3 minus 1 is 2, right? Minus 2, 1, negative 1. And then plug 2 in. So you have 1, negative 2, 1, negative 2, I guess. Yep. And then you have x1, 1, x2, 2 equals 0. And x1, 2 and x2, 2 equals 0. Okay, so here we used a second set of indices for the vector components x to distinguish the two eigenvectors. Yeah, so this is one eigenvector, and that's a second eigenvector. So first eigenvector, second eigenvector. Okay. Therefore, we can then write the two eigenvectors in the form of a 2 by 2 matrix X. The unnormalized solutions of these equation systems are oops. Right, remember they're columns. Okay. Note that we have obtained real eigenvalues and eigenvectors, but this is generally not the case when all elements of A are real. Normalizing the eigenvectors, finally. I'm kind of skipping some steps, but it's probably fine. Okay. So if the matrix A is Hermitian, symmetric, if real, then the eigenvalues are always real. Furthermore, eigenvectors for different eigenvalues are orthogonal. A situation might occur when the eigenvalue is k-fold degenerate. In this case, the k eigenvectors for this same eigenvalue are not necessarily orthogonal to each other, but they can always be chosen to be mutually orthogonal. We already know that eigenvectors can always be normalized. Numerical algorithms to determine them usually do this automatically and return an eigenvector matrix X that consists of columns that are orthonormalized vectors. As seen earlier, a matrix is unitary. So just recall unitary is X dagger equals X negative 1. Okay, so this is extremely useful. So for example, the symmetric matrix 2, 3, 3, negative 4 has the eigenvalues okay. Okay, so it says that the process, so this process, sorry, I don't know why I wrote this. Just showing that they're real, which is fine. So this process is called diagonalization. So, the determinant of a diagonal matrix is just the product of its diagonal elements, the product of its eigenvectors. Okay, so if we consider the eigenvalue equation and we multiply from the left with x, the inverse, so x negative 1 a x equals that. Now let us calculate the determinant on both sides of the equation. We use the fact that the determinant of a matrix product is the product of the determinants. Also, we use the fact that determinant. Okay, so we call determinant A B is equal to determinant A determinant B, and also the determinant of X. This is supposed to be a capital X. Okay. So it says, therefore, the determinants for x to negative 1 and x on the left side cancel each other out. And we obtain determinant A is equal to the determinant of lambda. In other words, the determinant of a matrix is just the product of all its eigenvalues. Yep. I think we talked about that before, actually. Oh, geez. Sorry. People were talking. My bad. It's like really hard for me to pay attention to chat when I'm like staring down and thinking very carefully. So using lambda as x, so this x, maybe I was doing something different. This x here or here is representing eigenvectors, and then the lambdas are always representing eigenvalues. And yes, it's a remarkable 2 specifically. I really like it now that I have RM view, but I would say that I wasn't using it every day when I didn't have this. Yeah, agreed. Also, how's it going? Tail-ass? I probably pronounced that wrong. There's a lot of vowels in there. And everyone else who's in chat. I recognize most of you. Okay, cool. So there we go. And we did this, and we're here. Yeah, let me move this back down for a second. I want to finish this thought, but I don't think we're going to finish these today. But there's a lot of fun stuff in here still. My goodness. Okay. Okay, so from this, yeah. So that's like something that we learned. Okay, so if I'm getting sloppy. Okay. So, yeah, we're on page 609 on to 4th paragraph, basically. Okay. So that's that. Let's quickly just do one of the eigenvalues in here and see what it returns, because I'm genuinely curious. So if we do t, let me move this because I can type a lot fast. I gotta go to work, so so 3. So if we have this and we solve for I'm guessing we get 2 tensors out of this, but I'm unsure. Bool. What is this Boolean? S eig eigenvectors, probably to like give us eigenvectors. So actually we can just close this now. So true, and our tensor is T. So if we make GHCI, make REPL, and we import homing pigeon, and then diagonalize T. So these are the eigenvectors, and it looks like it returns the. Okay, so what we really would like, it's returning the eigenvalues in a weird way. Did we write the eigenvalues down? I don't even remember. Oh, they were 2 and 1. Yeah. Yeah, right here. Oh, well, you can't see my screen anymore. But they're 2 and 1. So for some reason, instead of returning the eigen, man, that's so strange. This can't be right. It's doing something really weird here. Maybe it's mentioned. PyTorch. And we want to look up Eig. Okay, so are you doing this stuff now or talking about something you already know? Technically, I already know this, but it's been kind of a long time since I've done it. So it's kind of like a refresher. But I've done like eigenvalues and eigenvectors before. I have not done them in PyTorch, so this is definitely new. Maybe there's a linalg eig. Linalg eig. There is. And okay, cool. So let's try that one. Linalg eig. Two. What does this one do? That's better. That's much better. Okay, so this returns an actual vector of these things. And then, yeah, we get like the eigenvectors. Okay, this makes way more sense and is much better. So note eig is deprecated in favor of linalg eig. Okay. I don't think that's anyone's fault. Well, I mean, it's kind of strange for sure, but maybe there's a reason for that that I don't fully or like appreciate at the moment. So there we go. We've done an eigenvalue problem. And I think next time we're going to be we're going to talk a little bit more about eigenvalues equations. And then we're going to talk about basis vectors. And basis vectors is where like scalar products and basis vectors are going to get us a long way in chemistry. So that's kind of where we're going next. And then there's like basis and coordinate transformations, which are incredibly useful. Um, and then functions versus vectors. So that's going to be really useful. And then generalized eigenvalue problems. And that's it.